Okay, this is lecture 25 and this is the last lecture of our semester. So today, as announced before, we will talk about array subsystem. More specifically, we will talk about SRAM cells. So before starting today's talk, so let's review our previous lecture, lecture 24. So at the time, we have discussed about implementation of latches and flip-flops. So they can be used in sequencing static circuits, and latch can be implemented with a transmission gate. So by using a transmission gate, we can obtain the property of rail-to-rail swing. So our signal changes from 0 to VDD. After that, so in order to satisfy some desirable properties like input should be connected to the MOS gate, not the source or drain, and also static latches. So for that purpose, we introduce a feedback loop and immunity to the output noise. So for that purpose, we have also introduced another inverter to make a separation between the state node and the output node. So maybe you remember that the final latch should contain lots of additional gates for satisfying these properties. But anyway, we can build a latch. And also, a flip-flop can be implemented by a pair of back-to-back latches. So, for certain clock signal, using the clock bar and clock, we can just selectively sense the edge for lightning edge for our clock signal. So that was the implementation of latches and flip-flops. And the last lecture will be devoted to the memory, especially its SRAM cell. So now let's go to the introduction. So this one shows the categories of memory arrays, but I think that nowadays we have to more concentrate on this random access memory. So here you can find two important categories for our memories. One is volatile and one is non-volatile. So volatile means that if we turn off our system, then the memory is lost. And non-volatile simply means that even when we do not provide any electrical power, but still we can have the memory and later we can use it. So that is quite easy to understand. For example, if you have a USB stick, then you have a certain memory file inside your USB stick. Then after that, even though you do not provide any power to your USB stick, but later you can read it. So it is quite obvious that this seems to be a memory. However, in the case of this volatile memory, if you just push the button, power button of your laptop, then actually the data you have inside your computer memory is lost. So for some sense, volatile seems to be quite contradictory to the meaning of memory, but that is actually widely used in the realistic case. Even in this volatile memory, we can find two different categories of representative categories of our volatile memory, and one is static RAM, so SRAM, today's main topic, and one is DRAM. So what is static and what is dynamic? So in this sense, maybe you remember that. So we have talked about the flip-flop or latch. Yes. So here we have latch, and latch can be a dynamic latch if we use transmission gate. So simply speaking, when we have a certain output state, so say that transmission gate, and when we have a certain output state output, then if it is not supplemented by a feedback loop, without this feedback loop, eventually the leakage will destroy the state stored in this part. So that is called as a dynamic. And if you provide this feedback loop, then even though there is certain leakage, but the state variable will be kept safely. So that is meaning of static. So quite similarly, the meaning of DRAM or DRAM, dynamic RAM or static RAM means that if you have a certain memory, so a certain memory stored in X node, then dynamic RAM, DRAM, does not provide any feedback loop to sustain its value. And in the case of static RAM, we provide a feedback loop to keep its value safely. So that is the difference between SRAM and DRAM. Then you can easily understand which one is my question is which one is more complex and which one is more so simple in the sense of number of transistors or number of cells, structure of its unit cell. You can easily understand this one will contain more gates, more transistors, and will be more complicated. And yes, DRAM will have a much simpler structure, cell structure. So simply speaking, in case of memory capacity, so how much of information can be stored for us or for given SRAM device or DRAM device, then certainly DRAM has a lot of more advantages over SRAM. However, also there is another one like DRAM should be constantly refreshed. So, let's say that you just load certain information. After that, since this is DRAM dynamic, after long time later, so typically the time scale is just 10 seconds or a few 10 seconds. After that, you just lose its memory. So although you load one, after for example 1 day later, if you just check whether that is 1 or 0, then it will be 0. So if you just stay too long, then that information will be just diminished. So that's the reason why in the case of DRAM, you must always refresh your data. Means that the load 1, after that, for example, a few 10 seconds later, then check whether it is 1 or 0. Of course, since the time scale is not that long, so you will find this is 1. However, when you read this 1, the point of DRAM is this is destructive read. I mean that you load 1, and when you read 1, then you find 1. However, after that, if you read once more, then this is no longer 1. Your data is just lost and it becomes 0. So what you have to do is, okay, I just read. After that, I just write once again. Which data is written? Just 1. So in the case of DRAM, you frequently read just to save your data, or in order to just keep your data, you must read and write, read and write. So at first glance it sounds really ridiculous, because we are now talking about memory. However, the memory is not perfect, so always that should be refreshed and rewritten again and again. But no, at first glance it sounds really weird. So I felt the same feelings when I was first exposed to this information. But that's true. So you must always spend some effort to refresh it. But why do we have steel DRAM? So since it has absolute advantages in its capacity, if you wanted to have a large memory, then you must adopt this DRAM. So that is one thing. However, in the case of static RAM, so although its capacity is much smaller than this DRAM, but there is also another property. This is SRAM. SRAM can be integrated into our chip. So simply speaking, if you have a certain chip, so there is some blocks for your logical operation. Then now think about certain SRAM and DRAM. So from its own fabrication procedure, SRAM can be easily integrated into this same logic chip. However, unfortunately, in the case of DRAM, it cannot be integrated into logic chip because it requires really a specialized fabrication procedure. So, so SRAM is just placed quite close to its logic chip, or actually integrated into it, and DRAM should be separated. Then what happens? So the distance determines the distance determines the, how can I say, the speed between this information communication. So writing something into DRAM and read something from this DRAM should be done this inter-chip interconnect and wire, and instead of that, this SRAM is just nearby the CPU or logic, so it can easily communicate to this SRAM. So simply speaking, if you really need some information which is really frequently used and referenced, then that should be placed in this SRAM. And if you have certain large amount of data which is quite important, however too big to be included in this SRAM, then that should be placed in this DRAM. Of course, if you have certain data which is seldom used, not frequently used, however, if you need really huge amount of data, then that should be placed in your USB or non-volatile memory. So now, depending on the distance from your logic and depending on its speed and depending on its capacity, we can find out many different memory uses. Of course, we have a dream. As an engineer, our dream is to make a certain universal memory which is quite fast and easy to fabricate and CMOS compatible and whatever. Every beauty of these memory cells can be dreamed into one single device, and there have been so many candidates for that universal memory device. However, unfortunately, they spend quite a lot of time on that. Unfortunately, right now, people now realize that there is no one tool, one memory cell which is solve all of a problem. So therefore, we must keep this memory hierarchy still, but we can find so should have appropriate device for appropriate uses. So that is current uh, strategy of our society. Okay, so please note that this is LAM. So we have talk about LAM, and LAM means that we can directly access any information inside this memory cell. Say that if you have a matrix, and if I ask you some certain question like what is the value of 3,4 component of this matrix? So if you have a LAM-like capability, then now you can just go to this 3,4 component directly. However, in the case of any other memory device which is not called as other one, then you don't have any access, direct access to individual component. So that is really difficult to do that. So for example, you can say that serial access memory, that is not possible. This navigate in a random way. Instead of that, it should just let in this way or other predefined way. So of course, compared with this random access memory, this kind of a memory access type is much more inferior. So you may be curious why we have such kind of a strange memory which cannot be directly accessed. However, please note that that has also its own advantages, and also you know that that is also determined by the technological limitation. For example, so this kind of thing, they looks quite obvious, and also for example, you know, NAND flash, that is quite much used for your USB stick. However, you can find that there are so many other devices not being used in these days. So they are all corresponding to the category of non-volatile memory. However, depending on the progress of technology, so they can be many different forms. So if I ask you why we must use this memory, then at the time we had no flash. Simply. So if we have a better memory cell, then we can of course move to this better one. However, so that is also related with the progress of our fabrication technology. So I remember that when I was a undergraduate student, so there was no NAND, and after so during my term project for certain electronics experiment, we had to write a certain hardware. So I remember that I just programmed the chip and give it to our TA, and TA just baked it. Literally, he he baked the chip, and he just warned all of us, do not approach it to this baking machine. So if you make something wrong, then this baking machine is so sensitive, then it will demolish your entire term project. So I remember that, and some of our chips went wrong. So you know, that was really thrilling experience. However, nowadays you never experience such a kind of situation because you have much better memory cells. So anyway, so I wanted to say that, okay, we have so many memory cells. However, as a representative one, we will talk about today SRAM. And SRAM, you know, this can be made of just conventional CMOS technology. So that's the reason why I'm talking about SRAM today's lecture. So in volatile memories, so there are static structures and dynamic ones. So static means that SRAM, and dynamic structure is DRAM. In the case of SRAM, so we use feedback, and the state is maintained, and DRAM, actually there is no feedback loop. So it is frequently written or drawn in this way. So here we have one access transistor, and here we have one capacitor. So we have it. So later you will find that there is this is quite common for our memory array. There is one line, and here we have another line running vertically and running horizontally. Of course, um, vertically or horizontally, just to corresponding to this drawing, but this is conventional way we draw this system. And usually this horizontally running line is called as word line, and this one is typically called as a bit line, but anyway. So then say that now we wanted to write something. Write something means that here something is the 1 or 0 in this capacitor node. So simply speaking, if you wanted to write a logical number 1, then you just charge your capacitor. That is write 1. And if you just write 0, then you just keep this voltage close to 0. So that is written 0. So that is not that difficult. Then how can you increase the voltage? So simply speaking, if the node voltage of this capacitor is 0, then this is corresponding to information 0. And if this is close to certain your voltage, high voltage, then this is corresponding to 1. Then how can you make such kind of thing? How can you actually, simply speaking, making it to 0? That is quite easy. Just leave it, then it will anyhow approach to 0. Then how can you keep it to number 1? How can you apply high voltage to this node? Of course, this capacitor is working as just a disconnected line in its DC case. So now you understand the only way you charge this node is just to apply high voltage, high gate voltage to this MOS transistor, and now you have a connected channel, turned on channel, and also keep your this node voltage to high. Then what will happen? Now this is high, and previously you had 0. Then this one is working as your source, and this one is of course gate, and you have a high gate to source voltage. Now it is charged, and after that it is approached to which voltage? So voltage between your, for example, so we say that VVD minus threshold voltage. After that, now your transistor is turned up, and you will have a relatively higher value of your capacitor node. That is actually the charge collected in this node is regarded as information. After that, when you read it, what you read is, now let's say that you have a certain amount of charge collected at this node. Then when you read it, then you just say keep this line in a low level. Then let's say that you have relatively high voltage of this node. Then if you just lead this current, then what will happen? If this is close to 0, then you have a sufficient gate to source voltage, and your drain voltage now seems to be quite high. So what will happen? So there will be discharging through this line. Then your information will be led by our circuitry, but unfortunately once this kind of current conduction or discharging is occurred, then actually your information previously stored in this line is now gone. So if you try to read once again, then what you will read is just number 0. So what is it? Once again, this read is really destructive. You just destruct your current information and then get the current value. So once again, in the case of DRAM, you must write this LED information once again. So okay, it was 1, but it was now lost, so I have to write 1 again. That is refresh and write. Okay, so yes, that is the one. SRAM are faster and less troublesome. So less troublesome means that actually in the case of DRAM we have such kind of a problem, so we must provide refreshing, but obviously it requires more area per bit than DRAM. So you know that DRAM is actually the ultimate goal, ultimate form of memory cell. It has only one transistor and only one capacitor. This is the ultimate goal of our device. Of course, people try to even reduce this one to, for example, one transistor and no capacitor, because they feel that this capacitor is quite much troublesome. But many trials for reducing the number of capacitors from 1 to 0 was not that successful. So even nowadays, so as of 2023, we are still using one transistor and one capacitor for our DRAM. Okay. Then in the case of SRAM, how many transistors are used? So if we count the number of transistors used in a single bit, then please guess. So in the case of this DRAM, it was 1T, 1C. And in the case of SRAM, it is 60. So you know that, wow, the number of transistors is 6 times larger, and also about that 1T, 1C. Then you may say that, okay, although we have here 6 times difference, but here we have one capacitor, so maybe the area ratio is not that high. But please note that actually this 1C is usually integrated in a way like below our transistor we place our capacitor. So from the viewpoint of top view here, if we have a look at it, then actually this capacitor and transistors are vertically placed, and it does not consume any further area. So since we are now talking about the area consumed by one bit, so it is much more area efficient than this SRAM. So that's the reason why we are using DRAM for higher and higher memory capacity. Okay, do you have any question up to now? So if you have any question, then please let me know. So now let's go to this way. So this is memory architecture. So memory architecture means that so usually we have this kind of two-dimensional array. And we use two different numbers to access certain information stored one cell. Yes, for example, here we write 0 or 1. Then we wanted to read whether this is 0 or 1. Or sometimes we wanted to overwrite regardless the value of 0 or 1, and now we wanted to overwrite it to 1. That is possible using this array architecture. So in this array architecture, we have certain lines here. Line. There are many lines running horizontally in this drawing, and there is also certain lines running vertically. So for example, for this one, so we have two lines running horizontally and vertically, and these lines are called as word line, and these lines are called as bit line. So combination of this word line and bit line will uniquely specify the position you wanted to access. And you know that, so one thing is here. For example, let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. Here we have 16 rows. Then how can we access a certain row or certain word? So it is given by just 4-bit address. For example, 0000. If you have this 4-bit address, it simply means that we will activate this very first line. Only this very first line is selected, and all of our other rows are not selected. This kind of thing can be done with our decoder placed here. If we have a certain n-bit decoder, then we can select one of e to the n bit. So we have 4, so it will become 16. So we can select with this address, so we can select one of them. Usually select means that we apply, for example, high value, high voltage to this word line. Okay, that is one thing. So let's think about the read operation. Then if one word line is selected, then their stored data is just read, and it is transferred to this way. And here we have column circuitry, and we process this information. For example, let's say that there was the data written as 1011. Then when we read it, if we just selected this row, then the information is just retrieved in this way. Now let's consider more specifically the SRAM. So SRAM has many attractive properties, denser than flip-flops. So what is it? flip-flop just to keep the data sensed at the leading edge. So you can use the flip-flop as a memory. So once you just apply the, how can I say, the leading edge, then the data is sampled. After that, as much as you just provide the signal and clock is remained constantly without any falling edge or any rising edge, then you will keep the data. However, in order to implement the flip-flop, please remember that you must just introduce a series of your latches, and latches takes a lot of transistor already, so flip-flop is quite a large one. However, in the case of SRAM, as you will find that, so SRAM requires just 6 transistors. So although it is not as efficient as one transistor and one capacitor like DRAM, but it is much more efficient than our flip-flops. And another one is this is a comparison with flip-flop, and here we have a second line which state compatible with standard CMOS processes. It is the huge difference between our DRAM and SRAM. DRAM is not compatible to the standard CMOS process. So that's the reason why they have to have a separate fab. So memory fab and logic fabs are strictly divided, so they do not share. Actually, they do not share the material even. For example, in the case of logic, we can try many different methods. However, that is considered as a taboo in the DRAM fab. If we use certain new material, then that will generate a lot of problems in the case of DRAM. So DRAM is more conservative to accept certain new materials. So that is a huge advantages than DRAM, and it is, yes, it is faster than DRAM. Yes, it's true, and easier to use than DRAM. Yes, it has many good properties. However, in the case of a memory scene, actually capacity is the one of the most important one. So DRAM is much larger and cheaper. This is the very important one. DRAM is much cheaper for in terms of price per single bit. So therefore we have DRAM here. Of course, we have even cheaper one. What is it? Which one is even cheaper than DRAM? So that is NAND. Then the price of a per bit of NAND is much lower than even DRAM. So please think about in your laptop, your DRAM size, capacity of your DRAM, and think about your SSD. So you can easily understand there are several orders of magnitude difference between size of your DRAM inside your CPU or your mainboard and the size of your SSD. There is really huge difference. Okay, so now this is the standard cell called 6 transistors SRAM. What is it? So although it looks quite complicated, basically it is just a loop of our inverters. Okay, here you can say that this is one inverter and another inverter, and they are making a feedback loop. Of course, if we have only these two inverters, then mm, nothing can happen. We cannot write and read. So therefore, we must provide certain access transistors here and there. So now we have 6 transistors because it consumes 2 transistors and it consumes 2 transistors and one single, so therefore overall we have 6 transistors. Yes, so compared to the flip-flops, its memory efficiency is quite good. And yes, then compared with the flip-flop, how can you achieve this compactness? So it is important to understand that we have to introduce more complex peripheral circuitry for reading and writing the cell. Please note that in the case of a flip-flop, you can just provide just writing, then anytime you can write it. And also please note that it has well separated D and Q node. So you just insert input and not considering this D node. Once after you sample your D, then you can easily use your Q information. However, in the case of this SRAM, we just sacrifice this kind of input and output isolation. So using only word line and bit line, we try to write and read the same circuitry. Okay, so that is the reason why we have the compactness. So we achieve compactness. Instead of that, we have to introduce a more complex behavior of our circuit. It contains a pair of weak coupled inverters, yes, so cross-coupled inverters, and yes, they have relatively weak. Why we say weak? Let's say that they are so strong, so strong compared with this access transistor and access transistor. Then what will happen? We have no ability to change it because these two guys are too strong. So and they are really complementary. So if you have 0 and 1, then if they are so strong, this will be kept forever. So even though you try to disrupt this information 0 from 0 to 1 or 1 to 0, if this is weak, let's say that this is relatively weak and this is relatively weak, it cannot be changed. So therefore, of course, for static performance, we must have the feedback loop. However, that feedback loop should not be too strong. So it should be relatively weak because we wanted to eventually change it. Okay, so this one is you can now easily understand in usual hold case you have just a feedback loop. The data is kept, and when you try to read it, then you just read the voltage here. Since this is 0 and this voltage is red and this voltage 1 is red, so now you can say that there is a certain information stored as 0, and later we'll talk about the write operation. Okay. Now think about the read operation. Then how can we read this one? So now we say that the bit lines, so here now the bit lines, here we have a bit line. Why we have two bit lines? one line is called as a bit line and another one is a bit line bar. So this should have the complement one data stored in this bit, and they are both initially charged to high and floated. So although it is 1 and it is 1, so as drawn here, however, they are now floating. I mean, that how we can make this floating? So we have, let's say that we have a bit line, and of course, in this lower part we have a certain circuitry, and also in the upper part. Oh, sorry about that. Okay, upper part we have also certain circuitry, and here we have a bit line. Let's say that this is bit line. Then how can you achieve this floating? So it is simply given by this lower one is just disconnected, so no connection to the ground is provided from this line, and this upper circuitry at the initial phase, it provides certain PMOS like capability. So there is a VDD or some like a bit line voltage, and it provides some connection to this bit line voltage. So once it was charges up to this bit line voltage, after that this PMOS circuit is just turned off. Then what will happen? Yes, although it is initially charged to bit line voltage, now the connection to the bit line voltage is now lost. So there exists only one line, one metal line, which is charged, however now separated from any lays like ground or bit line. So now its value is floating. Then now in this case our word line is asserted. Asserted means that it is becoming to 1. Then both of our transistors shown here and transistor shown here just to provide a connection between our bit line, floating bit line, and this storage node. And also this storage node and this bit line, they are connected. Then what will happen? Initially, let's say that it is 0 and it is 1, and after they are just connected, then what you will see is, okay, eventually there will be certain average between this voltage 1 and 0. So we expect that bit line voltage will decrease, not like exactly 0, because you know we have already pre-charged the bit line, so this 0 cannot drive our bit line voltage exactly to 0. However, it is true that the value is anyhow reduced from this strong 1. In the case of this bit line bar, now initially this is 1 and 1, so even if we take the average, then what will happen? Still we will have just 1. The point is, after this lead operation, this voltage does not decrease to exactly 0. However, what we can easily detect is, okay, now we have 2 lines, and these 2 lines shows a certain voltage difference, and this voltage difference is just detected by our ladder circuitry, and say that this circuitry just determines whether bit line is higher or bit line bar is higher. if bin line bar is lower than bin line is lower than bin line bar, then we can say that the stored information was 0. And if it is 1, bin line bar is lower, then we say that the information was 1. So are you with me? So simply speaking, we sense the difference of two bit lines, and that difference was originated from the difference of stored data in this node and that node. That is given by this one, this difference. Yes, so simply speaking, one of the two bit lines will be pulled down by the cell. In this case, this one will be pulled down. Then, of course, you may say that, so this is, since this is 1, so our goal is, since this is a lead operation, we still want to keep this value equal to 0. In this case, in this inline bar case, there is no contradiction because this is 1 and this is 1, so therefore there is no driving force from this N4 device. But in the case of N2 device, there is something. Now, for N2 case, N2 transistor, its gate is high and its source is 0 and its drain is 1. What is it? Oh, now our N2 device is fully turned on. It tried to charge this anode. Wow. However, do you hope to have the transition from 0 to 1 in this operation? Now let's say that you wanted to read this information. However, if A becomes just 1, then you are now losing your stored information. That is a very undesirable case. Then which one? Just keep this value as 0. So please note that in this case, you must also consider another one. Like now this is 1, this is 1, 1, 1, 1, and you have 1. Your N1 device is also turned on and its source is grounded, and here you have a certain node. A node can be regarded as also the drain of your N1 transistor. So from your N1 transistor, N1 is fully turned on and it is drain. And also from this N2 transistor, this can be regarded as a source of also fully turned on N2 transistor. And now these two transistors are fighting each other to determine the value of A. Now let's say that if A, N1 is much more stronger than N2, then of course A will be kept as just 0. However, in the case of comparable N1 and N2, then what will happen? There will be the increase of A voltage. However, if A voltage becomes too high, then after that, the logical value will be just flipped to logical number 1. This is really undesirable one. So for lead stability, we must have relatively strong N1 transistor than to access transistor. That is the condition for lead stability. And now we wanted to talk about the right operation. So here we have something like this. So write operation, in the case of a write operation, still we assume that initially we have 0 and 1 configuration, and what we do is, let's say that we wanted to write down 1 to our storage. So previously there was 0. However, now I wanted to write 1. Then in order to write 1, we just provide 1 to this node and 0 to bit bar line. Okay, so then quite similarly, word line, the selected word line is raised. Then what will happen to this case? In this case, actually, the write operation happens not in this bit uh, n2 and n1, but it is given by this line. So now bin line bar is kept as 0 and word line is asserted. So now our N2 device is now turned on. It is on. Therefore, this N2 device try to pull down the value of our storage node A bar. And of course, this is counterbalanced by our P2 device. P2 device is always try to keep it to logical value 1. So if our P2 device is too strong, then N2, N4 will fail to pull down its value to 0. However, if P2 is so weak compared with N2, then when they fight each other, then eventually N4 will win and we will have the flip from 0 to 1. Once this information A2 node is flipped from 1 to 0, then using this feedback loop, then after that this initial 1 will become the later value 1. That is the way to write down our new value. Okay, so in this case, writability just state that our access transistor should be stronger than our P MOSFET. So now you understand, in order to satisfy both of read stability and writability, we say that our NMOS should be the strongest, and also our access transistor should be stronger than our P MOSFET. That is their expected the relative strength of these three transistors. So this is summarized here. So in order to make the correct operation, we must have this kind of thing. This one, MOSFET is the strongest and the intermediate value for access 1, and PMOSFET should be weak. And now let's have a look at the SRAM layout. So this is the SRAM layout, the old one. Where can you find your transistors? So please have a look at. You can find your transistors. For example, here you have your PMOSFET, and here you have a PMOSFET, and here you have your NMOSFET. So they share the same input, and that is feedback to yes. So this is input, and it is originated from the output of another the other inverter, and also the output of this left inverter is feedback to input of this right inverter. So they are making the inverter chain. So cross-coupled inverters can be seen here, And you know that we need two more access transistors. And where can you find these access transistors? And this access transistor can be found here. You have two access transistors. So now this is an MOSFET, another N MOSFET. Please have a look at your layout, and this is another SRAM layout. Or the main difficulty of this layout is, please have a look at this green line here. You have a green line. This is nothing but your well, and well has the shape like this. It's not a straight line, but it is just bended with 90 degree. So it is very difficult to actually make it. Instead of that, we just wanted to draw something like just a rectangle. So that's the reason why we have introduced another type of layout. And once again, you can find that this is corresponding to your N MOSFET and access transistor, and also you can find that this is corresponding to your N MOSFET and access transistor, and this central part is corresponding to your P MOSFET. Okay, you can just have a look at it, and you know that SRAM is really important for our logic system, because SRAM really takes a lot of area. I mean that when you make a certain chip, always you wanted to put more SRAM, because more SRAM is directly related with the improvement of your chip performance. Because if you have a larger SRAM, then there is less chance of missing your hit. So when you try to find out some information for your SRAM, if your SRAM is large enough, then you can store many important information. If you don't have enough SRAM, then what will happen? You try to get certain information, then your SRAM says that, oh, I don't have it. Then after that, once you detect this failure, then you have to also try to find out information in your DRAM. So that will introduce a lot of overhead for your operation. So always, if possible, you wanted to include as large as SRAM into your system. However, SRAM takes a lot of area, so that's the problem. Always we try to reduce the cell size, SRAM cell size, and previously it was continuously reduced. For example, think about this feature size. So from 100 nanometer technology node to 32 nanometer node, what is the difference? It is roughly 5 times reduction of feature size, 5 or 6 times reduction. And please have a look at the reduction of area, cell size. It was starting from 5.6 and it is now reduced to 1.16. Then what is the ratio? Its ratio is larger than 30 times, not like 40 times, but it is larger than 30 times. So you can easily understand the reduction of cell size is precisely following the square of this feature size reduction. Since we have 6 times shorter length scale, so just 6 1 over 6 and 1 over 6, that will give you like a 1/16th reduction in the cell size. That is rough estimation, and that has been achieved up to this 32 node. But where are we now? Are we in this 32? What is the advertisement from our foundry companies? We are now living in the era of 3 nanometer, so seemingly 10 times shorter than 32, and say that now please try to estimate the expected cell size. If it is really true, then we have more than 10 times the reduction of feature size. So then it will give us almost 100 times reduction. So if we just write down, if we just believe it, then we will say that the cell size would be 0.0016 micrometer square. But everybody in this room understand that is not the situation. We are now showing the latest SRAM, which was announced in our previous IDM, so 1 year ago, and its area is, so it is smaller than that previous one. However, it is 0.021. What was our expectation, extrapolation from our 32 nanometer scale? That was 0.0016. 0.0016. So compared with this one, it's more than 10 times larger. It means that actually we say that now it is called as 3 nanometer. Actually there was no significant reduction in that length scale, but anyway, this is the case, and its area is still much smaller than previous one. And unfortunately, there is one sad news. Compared with its previous generation, actually this value is more or less now saturated, and we do not expect a drastic reduction of our SRAM size if we just follow the normal way to scale down our technology. So of course, so what is the current situation? All engineers are just stay and doing nothing? Actually not. They are actively working to further scale down their SRAM. So it is very important. And as the last slide of this semester, I wanted to show you this graph. So this is so-called static noise margin of SRAM. This is sometimes called as a butterfly plot, and it is simply drawn in this way. Draw one curve. So how can you draw this curve? Is you have node 1 and node 2. What is node 1 and node 2? This is, you have SRAM, you have one storage and another storage which should be complementary. So you just select these two node voltages. Then maybe you feel a little bit weird. What is the weirdness? So please have a look at your black curve. When we have a node voltage 1 equal to 0, now you have the VDD. And when you have a node voltage 1 equal to VDD, since this is just a cross-coupled inverter, you expect exact 0 value. However, this curve does not show such kind of thing. Is it then something wrong? Actually, in the case of our SRAM, when you say static noise margin, there can be different scenarios. So among them, this one shows just so-called lead noise margin. Lead noise margin means that here we have a pin line and pin line, and say that mm, um, say here we have a storage 1 and storage 0, and we we lead this voltage and that voltage. Then what will happen? Yes, if this is the initial condition 1 and 0, and this pin line will kept as just 1. Yes, however, you know that in this case we will have lower value as an action of this stored 0. However, you know that since it has a finite size and it has a finite drivability, this voltage never goes to exact 0. So that's the reason why we have remaining value. This value is determined by the strength of our inverter chain and the amount of this pin line capacitance. So that is given here, and the size of the intermediate range, this one or that one, is determined as the noise margin. We believe that if this is large and this is more stronger to the perturbation to its signal. So the TSMC advertised that they're in their new technology, even with 0.45 volt operation. So when you say where can you find the 0.45 operation? Yes, this one. Yes, this green line is corresponding to you are operating your SRAM with 0.45 volt, and still you can see that certain noise margin which is given by 97 millivolt, quite close to 0.1. Since VDD is just 0.45, this is quite much, so it means that even with this low power operation or low VDD operation, we can have the working SRAM. So what is the purpose of showing this one? And it is now the company advertising that, okay, since this SRAM can be worked in such a low voltage, so now you can save your power consumption significantly. That is the main reason of this kind of low voltage operation demonstration. Okay. So therefore, that was the last slide of our entire semester. So let me just wrap up this semester. In this semester, as I announced at the very beginning of our lecture, we have talked about some components of digital circuits. Mainly, it was static CMOS, and in this course, we are not much related with the design, but we just investigate each component of electronic circuit, so digital integrated circuit. The key was, in my opinion, the key was our CMOSFET is not a perfect device. It has P MOSFET and it has N MOSFET. They are mismatched, and they have capacitors inside it, and yes, and they have certain voltage margin to be turned on and turned off. Also, they have leakages. There are tons of non-ideality in this device. However, within that limitation, people have developed a way to optimize it and to minimize the delay and power and minimize the area. That is the art of digital integrated circuit. So I hope that this course will give you a certain clue about what is the building blocks of digital integrated circuit. Okay, if you are interested, then you may enroll other courses in digital integrated circuit or circuit design or device technologies. Okay, do you have any question? If you don't have any question, then let's meet once again in this Friday, 9 o'clock. You will have a 90 minutes long final examination. Okay, thank you. Bye.